I am a first year MSc Physics student studying at Savitribai Phule Pune University, and my partner here is Sanket Bangar. But I think due to some unavoidable reasons, he couldn't join with us today. But he'll surely join us soon. I think if not today, then in the next upcoming sessions. And we together were going to conduct a talk on antenna fundamentals and types of antennas. Now, you must be wondering that what is a physics person doing in antenna business, right? Most of the time, antennas is looked upon as an electronic science or an engineering subject. But it turns out that antenna is a wonderfully amazing object in physics point of view, and it allows you to develop radio telescopes. So till now, I think we have, I think Equinox people and also the RAS people have got quite a lot of exposure into what radio telescopes are. And most of the time we discussed about what is exactly receiving the signals from the sky, right? So this entire talk is going to be a brief introduction to various types of antenna fundamentals. And I'll tell you how I got introduced to this field and why exactly am I suited enough to give this talk to you. It's only because I have a bit more experience into these topics because I have been studying these topics in core detail for the past 2 years. The reason for that was that during my undergraduate years, okay, is my slide changing? Yeah, okay. Yeah, okay. So during my, has my slide changed right now?
Yes.
Yeah, okay, thank you so much. Okay, cool. So during my undergraduate time, that was when I was doing my bachelor's, there was an announcement from IUCA, that is the Inter-University Center for Astronomy Astrophysics, in collaboration with Raman Research Institute. And the announcement was for a SWAN antenna design challenge, which was Sky Watching Array Network. SWAN implies Sky Watching Array Network. And they required us to develop or to simulate an antenna for observing radio signals at very low frequencies. Okay, so naturally, a bunch of students, a bunch of us got interested because partially before this announcement was made, we were involved into some radio astronomy projects where our team built a 1.8 meter radio telescope, and it was a very amateur level project where we observed the sun because, as in when you will know, or you will have a bit of experience, you'll see that sun happens to be a very strong source of radio light. Okay, and especially at the Ku band frequencies. But for now, I will shift on to this main thing, which gave me the main introduction to radio astronomy and antenna designing in the first place. So this one challenge required us to design a novel antenna. That is, and there are various types of antennas that you can see here, which are already developed, right? They wanted us to develop a new type of antenna itself, which was a huge challenge. Okay. And fortunately, so we got good guides. We got a very amazing team, which I'll just show you over here. These are not the best photos of them. I'm not sure if they'll be happy if I'm putting them over here. But here I am, and here's Sanket. But you'll meet Sanket later on. And we got interested into this and we started learning about antennas, antenna designing. We studied about various antenna designing softwares. And fortunately, with the guidance of Professor Subrananta Krishnan, who is a pioneer in this field, we developed a new type of antenna, which now ranks third, or which is now in third position in India. Okay, this challenge was for all India level. And we are right now at the third position. Our antenna design, which you can partially see over here, is at the third position. Okay, we called it Libra, that is linearly polarized broadband radio antenna. And now we are in the process of fabricating it. Okay, so in all this period of fabrication, then designing, simulating, I learned about this antenna design softwares, and I acquired a lot of information, lot of theory, all these things, and have a background of all those things. And of course, now I would be happy to share it with you guys and learn more, right? Because then we'll collaborate with each other and have few more discussions where you guys might be having a better understanding and we can have a good discussion on a few topics. So when we speak about antennas, today I will be covering these three topics. The last topic was going to be covered by Sanket. Let's see if we can reach there. Okay. So firstly, we will understand what is an antenna. Where does it specifically lie into our radio telescope domain? Because that is what we are really interested in. However, antennas bring up a very special part into all our lives because it happens so that we are able to communicate because of antennas itself, right? And as my guide used to always tell me that antenna engineers are the most paid people or most paid job in the country or anywhere in the world. Okay. But of course, we are right now interested into the radio astronomy field, and it is obviously a very budding, very growing issue because as you will read up on these topics, you'll see that GMRT is constantly upgrading their design, constantly putting efforts to make their design more better and better in sensitivity, and that requires a perfect design of antennas. Okay, and there are tons of parameters that will affect an antenna, and this is what we'll do into how does an antenna radiate. We will not focus on why it radiates right now. Probably we'll have a discussion on it, but I'll touch upon it briefly if possible. And then we'll move on to types of antennas that are already available to us, which are used throughout the communication era, throughout all types of basic use cases. Okay, so moving forward, what is an antenna? An antenna, in simple terms, is a transducer which converts electromagnetic waves, electric power to electromagnetic waves. All right. So electromagnetic waves happen to travel through vacuum and through any medium, and they have quite a high speed. And this is a good way of transferring power or information that we can now, with the help of antennas and the other circuitry, now we can convert electric power. We can convert the the information coming from as light into electrical signals and deduce something from it. Right now also we are constantly using antennas throughout. So what are the structural things that define a good antenna? So that is the physical structure of the antenna, which we will touch upon. Then the frequency range of operation. Whenever you ask an antenna designer or an antenna engineer and you ask them, hey man, can you build this antenna for me? Or I want this antenna. First thing he'll ask you, what is the frequency range? What is the vswr that you want? What is the gain that you expect? How much beam width? So all these parameters would come in, but the first question he'll ask is, kaun se frequency ke liye? What frequency do you want? So accordingly, I can build it up. Then comes the mode of application. Of course, this I will touch upon in detail when we come to the topics of gain, because mode of application is a big, as a broad phenomena, and I'll give you a very nice example why mode of application happens to be a very important parameter when you are designing antennas. Because, yeah, okay, we'll touch upon it later on. So coming back to our main thing, that is, what is the importance of radio antennas in astronomy? Okay, this particular slide will be in every session that you will attend, given by a lot of professors, a lot of teachers. This particular slide will always be there because this in one frame shows how important radio frequencies is for us. Okay, so to quickly explain you, because I think most of you might have seen this a lot of times, we see here that we have a large amount of area that happens to be perfectly visible to our radio waves, to the antennas over here in the ground. Okay, so these particular radio waves are not being reflected or not being hampered because of the atmospheric opacity that usually causes problems into gamma rays, of course, and into visible light also at times. Okay, and infrared is obviously submitted out. And interesting phenomena happens somewhere over here when over lower frequencies also we get these blockades. Okay, and this is very interesting because I'll tell you that as we saw in Swan also, we are looking for lower frequency information about some source in the sky. Now, why we are doing this, why we are approaching to a lower frequency, why not going towards higher frequency, is a beautiful concept that requires a lot of explanation. Okay, so I will not touch upon it, but to give you a certain nice explanation, here our atmosphere actually is trying to is hampering all those signals coming. So there is a lot of RFI. Usually, antenna experts usually talk about this term that is called as radio frequency interference. Okay, this happens because the atmosphere seems to be blocking or producing radio waves of its own because of the plasma charges available there. So plasma oscillations are the reason why frequencies below 10 megahertz also get reflected. This is widely used for wave propagation, actually, for remote sensing, but to observe radio astronomical data or the astronomical data, it becomes a problem. And partly, I have worked on this particular area, that is 10 megahertz to 40 megahertz. Also, for a space payload, it's called CMs. There, actually, we are trying to develop an antenna which will measure the RFI coming through these areas so that we could cancel it out for the ground-based telescope analysis. Okay, so we are putting that payload, specific payload, into lower Earth orbit so that we could measure the RFI over here, and it's going to be an interesting project. So I'll discuss about it later on whenever we get time. Okay, and yeah, questions we'll take towards the end because I'm not sure if I'll be able to complete whatever is required today. Okay, so let's move on. Okay, I'll briefly touch upon these. I will throughout the entire session, we will not be touching upon lot of mathematical equations, but this particular slide, that is how does an antenna work, relates, because this is does anyone know what these equations are called? I mean, most of the undergrad students must have seen this. Does anyone know?
Maxwell equations.
Yeah,
Maxwell's equation.
Correct. But people know these equations. People have, I myself have a dream of getting them tattooed on myself. But it happens that most of the people do not know what they actually mean. Okay. There is a very less intuitive understanding of why these equations are giving us what they are. People know their results, and sometimes I also feel that the mathematical complexity is so high that it masks down the intuitiveness of antennas or the working of antennas because of these particular equations. Okay, so we'll obviously discuss this if there is a personal session for the students in our group. That is, I think for Equinox, it is called radio simulations, where we'll discuss why these equations are giving us what they are, and why are we getting these radiations from, and how is electrical power even being converted to electromagnetic power. Okay, and for now, let's keep it simple. I'll give you a small simulation or a small animation where you can see that I have something called as the electric field. Usually we stick towards electric field. It is a convention. And what we can see happening over here is there is a voltage difference that is being generated across these poles. This specific thing is your antenna. And you will see that as the electric field is traveling through it, the voltage difference is being created, and that is being received by this resistance over here. Okay, so let's move forward. Okay, now we come to different characteristics of antennas, and this is what you will be if you are in the simulations group, or if you happen to get introduced to this field of antennas and how instrumentation works, you will be always be listening to these terms constantly and worrying about these terms. That is the gain, the directivity, the radiation pattern, impedance, which is very important, reflection coefficient, S11 visor. This is this is pronounced as vswr. So, okay, we'll call it vswr for now. Bandwidth, Smith charts, polarization, polarization of antennas. Okay, and we'll discuss them part by part. Okay, so okay, we come to gain. Okay, is this coming in the middle? Not sure. Okay. Yeah, so the gain of an antenna is something that we are taking out of. So right now you saw the animation of how the electric field or the changing electric field was producing a voltage difference, right? The same thing can happen other way around. So there is something called as the reciprocity theorem in antennas. I have not mentioned it solely over here because it is something very intuitive, but it has a very deep meaning. The reciprocity theorem says that if my antenna is a very good transmitter, that is, it is transmitting power very properly or in a very good fashion, it will receive power in the same fashion. That is, it will receive power in the same way. Okay, so what it is receiving and what it is giving out is basically measured by gain. Okay, the gain of an antenna is basically how much it is radiating out. So I'm not sure if you have read this out. I'm not going to read it, but this is a basic definition of how. And yeah, this is important that in a transmitting antenna, the gain describes how well the antenna converts input power into radio waves headed in a specific direction. Okay, so I should have explained you directivity first, but gain is a much more intuitive thing. The directivity of an antenna happens to be that most of the times what you will see in antenna is that it is directional. Okay. Here you will see that the gain of an antenna is measured in dBs. That is a logarithmic scale. I'm sure you have come across this term dB in your courses till now, or have you not? I mean, I'm not sure. We are all undergrads, right? Yeah. I think most of you must have gone through what is dB. dB, if you want a short introduction, it is just a logarithmic comparison, and it makes our job very easy because then our multiplications become additions, and we don't have a problem if we want to find out something like a difference between 10 to the power minus 18 and 10 to the power minus 19. Okay, this mathematics becomes very easy when we are having logarithmic type of scale towards it. Okay, and this dBi over here is a very particular case because usually an antenna has an isotropic gain. What an isotropic gain means, it is antenna uh, when we consider an antenna to be a point, or when we consider it to be a single source, okay, not having any length element, it will radiate out in all directions equally. Okay, and this is called as an isotropic gain of an antenna, which is usually not the case, obviously, because each antenna will have some kind of a directivity because of its length parameter and the resistance power, resistance element it has. Okay, so but this parameter becomes useful because then we can compare our antenna with the isotropic gain. Okay, so here you can see that I have an antenna whose gain would look something like this. Then I can compare it with how much difference does it have from the isotropic gain. Okay, and this happens to be a very high gain antenna. It is a characteristic pattern of how a high gain antenna looks like, and we'll discuss it obviously in further detail. And then here comes directivity. Directivity becomes a very major issue because sometimes, as I think most of the RAS students would agree on this, that if our array had a field of view, the directivity would also mean the telescope's field of view, okay, or the resolution. If we did not have a single beam up and we had a dome kind of a scenario, we could never ever map the sources. Okay, we could not map it because I think most of you are familiar with optical things. We also tend to have a focused kind of a scenario, right? We do not see the broad picture, but in some instance, low directivity is also very important, and I think I'll discuss it properly once you see how these things change. Okay, so Okay, yeah, I've explained this properly. Yeah, so to study these things, we have something called as the radiation pattern. So this is a very interesting thing, and most of the people get attracted to antenna designing, seeing at these simulations itself. Seeing the radiation pattern is tremendously amazing and satisfying. Okay, and to this, I have simulated a bow tie and this is the dipole antenna. And here you can see it is a toroidal kind of a structure, right? It has a toroidal structure, and this is how an isotropic gain looks like. So over here, yeah, I'll have to explain what is omnidirectional also. So omnidirectional means that it is radiating out in all directions, but in a specific way. So here you will see that there is a null point, correct? For a dipole over here also you see that there is a null point, but it is radiating in all directions apart from these, right? Are you able to see the difference that there is an isotropic gain that is in the entire sphere, the gain is constant, but in omnidirectional, yes, we have directional property or the gain in these directions, but here it becomes zero. It goes on to zero. Okay. So these are pictures. This is what I have actually simulated. It's very simple. Once we start simulating these antennas through, we'll understand more about them. Okay. This I'll explain. These are properties. These are the specific things that you need to understand when you're looking at a radiation pattern. Okay. So this is the dipole antenna which I simulated, and I put a small animation for it. This was actually tuned in, which is what we say, which was made specifically for 20 megahertz. Okay, so now I'm not able to stop this because if it's a GIF, I think. But at 20 megahertz, if you could observe, it is having a quite positive and a nice gain structure. And if you are getting confused by this, this is called as the ground plane. I think I'll explain this if time permits, but right now it's not required for us. So all it's doing is it is just shifting all my radiation towards up. Okay, it is having an upward radiation. Ground plane is obviously important, and we will have a short discussion on it. Usually, when we are studying this, quite hello. Hello.
Yes, sir, your screen.
Yeah, your screen is visible.
Yeah, I think there was some kind of a crash I had. I'm not sure. Till where did you hear?
Till antenna simulation.
Till antenna
That
simulation.
animation.
Did you see the radiation pattern?
Yes, yes.
Okay, cool. Okay. Okay. We are over here, right? Okay. Yeah, good. So usually what we study is something called as the polar plots, because anyway, how much ever attractive this looks, right? We have to study what is the radiation pattern, and to study we require 2D plots because it becomes simple for us. All we have done here is we have just taken a cross section and we are looking at it through a polar kind of a scenario. So I'm not sure if you are able to properly understand, but see, are you see it properly? So the 0, 30, 60, 90. So it is a complete pattern from here to here that we are seeing in 180 degrees, and 0 is termed as the zenith for now. Okay, we can obviously manipulate it according to our need. And this I wanted to show that this
Excuse
over
me,
here
sir.
is the gain at 10 megahertz. Hello.
Excuse me, sir. Your slide has not changed yet.
Which slide are you able to see? I am showing the polar plots. Are you able to see the polar plots?
No, it's antenna fundamentals. Home.
Was a circular image that you were showing, the far field one.
Hello?
Oh,
Yeah, I'm not able to hear you properly. Hello?
We are seeing the polar plots.
Yeah, you're seeing, yeah, I'm explaining those only right now. So I'm not sure. Okay, what I'll do is I'll switch off the video because it is taking too much bandwidth, right? Okay, Zoom not responding. Wait. Technical problems make it all go wrong. Okay, Sagar, I'll try to rejoin again. Is that possible?
Yeah, Viren, yeah, you can rejoin.
Yeah, okay. Yes, hello, am I audible?
Yes, sir.
Yeah, okay. Okay. So, yeah, I'm going to start my slideshow then. Okay. Yeah, now it's working fine. Yeah, so I was explaining the polar plots. Can someone tell me where you last saw? I was explaining this particular polar plot. Were you able to listen to it? Okay, I'll anyway repeat it. It's not a problem. So this particular, if you observe this particular polar plot here, right? So this was very near to our tuning frequency. Therefore, it's showing a very clean diagram. This is what we call as a clean polar plot, where there are no nulls here. That is, there are no dips in the middle. However beautiful these patterns are looking, they are not something that we want. Okay, so we can clearly see that at higher frequencies, the dipole antenna is actually not functioning very well because it is not radiating efficiently in all the directions properly. Okay, and this is what we need to avoid. So, okay, so to study this particular thing in, and we obviously want to put some numbers on how do I know that I want a specific thing about an antenna, that is about a specific gain, or how much gain do I want in what direction. Then we are supposed to find something called as the beam width. Okay, and beam width is basically something in an aperture angle. It is an angle where most power is radiated. Okay, and we usually want this power to be in a directional form, but it is not always necessary. And now I will put this point to conclusion why I'm saying this always, that it is why it is not always required that an antenna should be directional. Okay, so I have two examples, or rather, a single example would just figure it out properly. But let's have two examples. One would be a telescope or radio telescope itself. If I have a very high beam width, or for now we'll say that it is omnidirectional, that is, it is radiating in all direction. We do not know where specifically power is coming from. We would never map the sky, right? That is what I mentioned now. But this phenomena is very useful in GPS. Why so? Because what happens in GPS is our cell phone exactly has a omnidirectional pattern. Okay, if you ever try and see at that particular band, we have an omnidirectional pattern. Why this happens is because the GPS satellites, many satellites are trying to triangulate your position. Okay, so it is not a good practice that my antenna would be directional in one sense, right? And then only one or two satellites will be able, or one or two satellites will be able to catch my signal, and it won't give you a triangular spot. The triangulation won't happen in a very effective manner. So this is where you would require a directional or an omnidirectional antenna, because now I want information from all sides. All right. Even the project that I mentioned, the CMS project that we were building, I was shortly a part of it. We were trying to develop an omnidirectional antenna itself for that purpose, which would go there and take readings. Why? Because we want readings from all the ends. We are not looking for specific kind of a radiation or specific source. We are checking the background. Okay. So this is where the beam width becomes a very big crucial factor, and we usually say that we are trying to measure it at half power beam width and first null beam width. What is this half power beam width? I think, yeah, this explains it in a better fashion. Half power beam width, simply the name tells you that wherever my power becomes half, so that is basically what I'm trying to trace. Okay. And what it basically gives me is that in this particular angle, my power will always be more than the half of my maximum value, which is over here. Okay. So the half power bandwidth is, suppose my gain over here is 10 dBi, okay, or 10 dBs. And here it would be so something around 5 dBs, and I plot a line here. This becomes my half power bandwidth. So half power beam width, sorry, not bandwidth, beam width. Okay. So my angle over here, which I will subtend, will become my half power beam width. And you usually, for radio telescopes, from what I have studied, they usually prefer that it is roughly around 30 degrees, 10 degrees, however directional you can get it. But of course, for practical reasons, this is going to change, as you saw, with frequencies. And to develop a wideband antenna and to keep it directive throughout becomes a big problem when you are designing an antenna. Okay. And when you are whenever you are observing the structures, I'm sorry, I put a ground plane there, or else you would have seen these particular side lobes also coming up into the picture. So if you remember the polar plot, we had some kind of a structure, and we were splitting that structure into a small parts, right? Those were actually our side lobes, and they usually don't look as symmetric as they are looking right now. And they are a big problem, because suppose I want to measure a source, or I am looking towards a source, and at this end, if my side lobe or my minor lobes are powerful enough to catch something over here, my system will receive power due to this and this also. Okay, and this becomes a major problem. Side lobe level becomes a very big problem for high frequency or for low frequency antennas. And because usually you will observe this whenever you will design, we will design this and we'll see this, that side lobe level becomes a big problem for low frequencies, and how you can manage it, how you can design an antenna in such a way that the side lobe level is minimum, and it also helps in our array analysis. Now, why it is useful in arrays? Because if you see in arrays, if I have certain directionality over here, and if my antenna, one more antenna is present over here, it will start interfering. Okay, we do not want that. We usually do not want this interference to happen. Okay, this might cause problems into arrays. So we have to take special care of all these things when we are designing these antennas. Okay, it is a very fundamental part of and these big projects like MWA, LOFA, even Gauribindo Radio Telescope has taken special care to actually reduce their side lobe levels and have a high gain at very low frequencies. Okay, Gauribindo works at a very low frequencies, actually 40 megahertz or so. Okay. Now we come to the most important part, that is impedance. Now it happens. Okay, till now everyone has followed, right? I was completely audible. I have to ask this because I'm not sure what happened to my PC today, laptop today, but it's okay. I think you guys are able to listen everything. So
Yeah, you were audible, Viren.
yeah, cool. Thank you so much. Okay, so we come to impedance. Okay, now it happens that our entire antenna can be electrically reduced or electrically simulated to be an LCR circuit on its own. Now, if you go to the fundamentals of why this antenna is radiating, you will realize that there are something called as capacitive. An antenna has a capacitive resistance, reactiveness, reactance. All these kinds of phenomena come into picture, and it has an impedance of its own. An antenna has an impedance of its own. Okay, and anything that gets an AC circuit, AC series, AC current or or a voltage is applied, alternating voltage is applied. What will happen is then it will have its own impedance and it will perform accordingly. Okay, so impedance is something that is measured in ohms, but it is not resistance only. It is something more, and it is actually it is actually a mixture of resistance and reactance. Now resistance is our very own friend, which we have been studying for since 9th standard or 8th standard. That is, it is essentially the friction against the motion of electrons. Actually, resistance in antenna is the most key part because that determines how much power will be radiated. Okay, resistance actually determines that, and you will appreciate this when you study Maxwell's equations or when you study what exactly is happening, what are these radiative reactances and etc. So we will, for now, we will stick to the simple things just to have an introduction of the important parameters. Okay, so resistance, something that we always know, and reactance is something, because I just told you that the entire antenna can be an equivalent LCR circuit. Okay, and it will have an impedance of, it will have an inductance of its own, it will have a capacitance of its own. And here you see a very important formula, that is XL is equal to 2 pi FL. What is important here is this F. You will have to appreciate that why high bandwidth, that is of I have not introduced bandwidth till now, but in the general sense you guys must be knowing what bandwidth is. It is basically that my antenna is functioning in the same way, it is functioning properly for a very high frequency ranges. That is, it is trying to maintain these properties in a specific manner, or it is manipulating its properties in a specific manner that it can act that can function perfectly through all those frequencies. And to do that, it is a very tough job. Okay, it is a very tough job. So to get a better idea why impedance becomes a very major issue, here I have a circuit, but for now, okay, yeah. So impedance usually becomes a complex quantity. I will not. Okay, if I can write it, it would be better. But yeah. Okay. So impedance usually becomes a complex quantity. So if I have said, I can write something like 50 ohms plus I times 50. All right. So here the real part actually tells me how much power is being radiated. So I'm just introducing this very shortly. And this actually tells me the phase. Yeah. You can basically draw a phasor diagram of it, and you can solve a lot of problems just by looking at it. So this is a very intuitive, very intuitive idea, basic one. So I was just wanting to tell you that impedances happen to be a complex quantity because I would require it further on. Okay, so now I have a circuit over here. This circuit tells me that I have some kind of a voltage source, and this is my antenna. Okay. Now we are acting antenna as a transmitter for now, not a receiver. Okay. So because I told you that we can just simulate transmitting antenna because they will essentially function the same when it comes to receiving part. Okay. So when we have this voltage source here and it has its characteristic impedance that is ZS, and we have an antenna whose impedance is ZA. Now, can someone tell me what is the best case scenario when the power radiated would be maximum? Have you guys studied about this phenomena in your 12th grade or somewhere else?
And ZS equal to ZA.
ZS equal to ZA, and one more condition. You are missing on one point. You are correct. ZS equal to ZA. I'll explain it why this happens, but there is one more point. I just gave you a clue, but 2 minutes before. What about?
Resonant frequency.
Yeah, resonant frequency. No problem. Okay. No. Not about resonant frequency. I'm saying I just gave you a clue about impedances. Usually impedances are not going to be real. So what will happen in that case? Okay. So for anyone who is not following, if we try to measure the power given by power emitted by this antenna, we get to this equation. Okay, you can use simple Ohm's law for this. And this specifically is for low frequencies. I'm telling you for now, although it won't matter right now, but for higher frequency, we get a much complicated equation. For now, we will stick to this equation, which is quite simple for us to analyze. And for this, what will be the maximum case? As he correctly pointed out, it would be ZA should be equal to ZS. Okay. In any case, that is when this is very, very small, or this is very, very small, or something is very big, or something is very small, it won't work because the antenna would not radiate in a most efficient fashion. All right, at that particular frequency or frequencies. So the important point that you missed was that is the impedance is can be a complex quantity. Okay. And in that case, my ZA should be a complex conjugate of ZS. Okay, that is the main part. I hope everyone understood why that is so. Right? I mean, it's very intuitive, but ZA should be the complex conjugate of ZS, and we write that in general. Okay, because if it's real, then it obviously becomes ZA equal to ZS. And this is something called as the maximum power transfer theorem. Okay, and it is the most important thing an antenna designer should realize and should understand, because I think the RAS students would appreciate it more, because we discussed it in recent Professor Ramesh's lectures, that you require a matching between the antenna and the circuit. Okay, you are receiving some power from the antenna. Okay, I have, okay, yes. So what the maximum power transfer does is, you are receiving some kind of a power, but now you want to go into electrical signals again. And this is where you want you want to grab the most information possible, right? And if you do not have, suppose here my impedance is something 75 and here it is something 50, which is mostly the case, 50 ohms, then it is not perfectly matched, and I would not get a very good receiving power, or my efficiency of receiving goes on bad. Okay, so this is Z antenna is equal to Z transmission line, which is usually a coaxial cable in our case. Transmission line is a very different theory, which is actually a basic for understanding antennas, a transmission line theory, but that again involves a lot of equations. So we will keep it to our own mentor discussions. When we will have short discussions on our own, we'll try to solve these Maxwell equations and get into how they are actually giving us a radiative field and all sorts of things. Okay, so moving forward, I will briefly touch upon what is called as the Smith chart. Actually, when we will when the projects for Equinox start, our basic idea is to design antennas. Okay, and check antennas for their performance at various frequency bands. Now, when this happens, we will have to understand that if I just told you that if it is not matching properly, then either it is inductive, either it is resistive or capacitive. is shown by this particular plot. This is a very interesting plot, how it comes into being, and we'll have some tutorials on how you can actually plot it, and the software does it very easily for us. This is something called as the prime center, and I'm just not giving I can't give you a very nice justice to explaining this because it will require a lot of time because you specifically need a tutorial as to how to point a specific impedance on this, and by that you will get a lot of information about the performance. So usually if you are to show if you design an antenna and you show the Smith chart, some antenna engineer would clearly see that, okay, in this part there is a problem, or your antenna is particularly not functioning. Why is it not functioning well? All the autopsy, I would say, of the antenna can be done through here. Okay, so now we come to the parts where our antenna would be judged heavily based on these parts, because whenever you are making an antenna, and obviously these parts will also reflect into Smith charts, and I'll explain it to you when we will discuss Smith charts. Okay, but reflection coefficient and VSWR are a very important parameter showing how good your antenna or how good your antenna is performing. Okay, so usually what happens is when there is a lag, what happens is when there is an impedance mismatch in the circuit, there will be standing waves that will be formed, and due to maximum power not being transferred, that is the entire current is not being transferred, there is some current that will be reflected back from my antenna itself. Okay, so if my load is over here, so there will be some part that will be reflected back again, and we have to try and minimize this reflection part that is happening. Okay, it essentially happens when our antenna is completely matched, but how we can match it becomes a geometrical problem also, because the geometry of the antenna would also decide how what is my inductance, what is my resistance, what is my capacitance. Okay, so that is where designing the antenna comes into picture, and VSWR is a very clever way of doing it. Now I need a video on for this. I hope it does not shut down everything. Okay, are you guys able to see me? There's a lag. Okay, so what is happening now in VSWR? In VSWR, when you basically have a standing wave that is coming, you have a wave that is input, and you have a wave that is output. Okay, that is reflected back towards the source again. This particular phenomena causes something called as the standing waves. Okay, the VSWR's entire full form is voltage standing wave ratio, and what we are trying to measure is we can actually measure reflection coefficient in a very simple scale by actually having note that this by actually not analyzing what is happening in the reflection part or in the or in the incident part. Rather, we can just study the standing wave itself and see how its amplitude is changing. Okay, and it is a scale basically which varies from 1, that is the maximum value should be 1, and here you can see there's a formula. You also measure reflection or return loss in dBs, and you expect it to be very, very low, that is -10 dB, -8 dB is expected. Okay, and VSWR should be roughly less than 2. Now if you go out seeing any antennas, okay, even your Tata Sky dish, these parameters will be written there. What is the input impedance? What type of cable can be attached? Any cable cannot be attached to the Tata Sky dish. You require a 50 ohm impedance cable or 75 ohm impedance cable. That is always written there. Without that, maximum power won't be transferred and you will not receive the specific things that you require. Okay. Now, whenever you go across or come across these terms, you should be able to know how exactly they are performing. Okay. Changing now. Has my slide changed? Yeah, okay. Now we come to a very important part, that is the bandwidth of the antenna. Not sure if am I running late? Okay. So in the bandwidth of the antenna, I'll quickly cover this part. Bandwidth is basically for how much period, how many frequencies is the antenna really functioning well. Okay, this is very important because as I told you, we are looking forward to high bandwidth antennas because we want more information from a single antenna itself. Okay, we are looking at high frequencies because and also of course we will decrease our time sampling rate also with band. Okay, I think most of the RAS students will appreciate this because we sample our readings or the readings, or we can resolve our readings to a point where it is 1 by bandwidth. Okay, usually. So we require high bandwidth so that our sampling time becomes very small and we could resolve it to a very smaller channels. All right, and this is basically a plot of a reflection coefficient, and you will see that over here it is becoming 0. 0 means it is ideally becoming a mirror. Okay, it is just reflecting everything that it is transmitting at 1.5 gigahertz, and you will see that it is really functioning between these 2 points. That is the minus 10 dB bandwidth is very low over here. Okay, and it has a central frequency of 2.5 gigahertz. So mostly this antenna, particular one, which the image from from antenna theory, is basically 2.5 gigahertz antenna, but it has a very slow bandwidth, and they have just tried to analyze it for a very large end because they wanted to show how my antenna is performing. Okay, and there is something called as the Q factor. We usually don't measure it because bandwidth calculations are automatically done through the software, and but it is a good thing to know how my bandwidth is, what is my bandwidth, what is my fractional bandwidth, etc. All these parameters. I'll give you the formulas for it. And these are the different types of antennas that, if time permits, we will discuss, or we will take it on through our next session. Okay. But basically, you will see that the different designs of an antenna will reduce or increase the bandwidth in a particular way. Okay. Now, what are these percentage bandwidth and fractional bandwidth? There is a simple thing, that is, fractional bandwidth would mean that the minimum frequency at which my the difference between the frequencies over which my antenna is working divided by the central frequency. And percentage would mean obviously to just multiply it by 100. Okay, so all these characteristics and parameters are given in every antenna. Okay, whenever you go out to see a Tata Sky dish now, or you go out to see there is a small LNB there, that is a low noise block, which has the particular antenna. So the dish would not have any specification. It would be written on the small receiver that is there. And there you will see all these specifications. Mostly they are written what type of cables, etc. are required. So you could go and check what and let me know what was the fractional bandwidth, what is the bandwidth required, what is the operating frequency of those signals. Okay. Now we come to the last part, that is a very interesting part, my personal favorite when it comes to antennas, when it comes to theory of antennas, because polarization is a subject that we usually learn in optical. Okay, and we do not, at least when I was first introduced to this, I did not understand why we would require polarization in radio antennas, right? But it turns out that specific radio, I would not go into the what exactly is polarization, circular, elliptical. That is a very generic thing. But in radio waves, polarization becomes a very important characteristic, and polarization studies is given the highest importance when it comes to radio astronomy. Why is it? Because certain mechanisms have a characteristic polarization. Okay, if you go on for, I think, I can't remember a particular example, but synchrotron, I think, has some type of circular linear parts. And what is funny part is, I'll ask you a question, okay? That can my can my antenna, which is linearly polarized, okay, can it receive circular polarization? Can someone answer? If my antenna is a linearly polarized antenna, can it receive circularly polarized?
I think no.
Okay, one answer is no. Anyone else?
Yes, I guess.
Yes. Okay. 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 We'll discuss why it happened, but I want someone else to answer. Okay. This you can just speak up. I mean, don't put it in the chat box. We are at the end of the session anyway, so you can just speak up. Do you think that a linearly polarized antenna, usually a linearly, how would a linearly polarized antenna look like? It would be a simple dipole between this and this. Okay. And what would be a circularly polarized antenna? It would again be a normal dipole or a circular loop, but having a common connection. Now, can you tell me if it would require if it would measure or it would receive circularly and linearly polarized light? Or if it does receive, what would happen to the power received? Can you tell me? Anyone? I don't know who is answering right now, but one answer was no. I would like to know why you said no. Can you? Who was it? It's okay. I mean, yeah, it's completely intuitive to say no, but the correct answer would be yes. It would receive. It is not. It is not necessary that yeah, I would not receive any linearly polarized on a circular end, because if you see that only one component of my linear polarization would be seen. So whenever I am seeing at a a circularly polarized radio wave in a linear polarized antenna, I would see only one of the aspect of it. Okay. Usually people confuse this part to be only electric and magnetic fields. This is a very big confusion which even I had. I said that, hey man, if this is electric field and it is going through, then I would receive only this part. This is going to be just magnetic. That's not the case. People. This is the electric field itself, which is the electric field vector itself, which is rotating and forming a locus around the line of propagation. Okay. Many people have this doubt. I'm not sure. This might be very trivial for you, but I was under this impression. So, yeah. Okay. I think. Do we have time, or can we continue with types of antennas? Or should we end it for today and take a few questions if I can answer? Hello? Yeah, guys, let me know what should we do. I can go about just showing you what are the different types of antennas. We have a list of them, but this can be discussed in a very nice detail by Sanket. Okay, he's also one of my teammate from Swan, very enthusiastic about antennas. Actually, he's currently doing a project on pulsars under Avinash Desh, okay, Deshpande, and he would also be very would also be wanting to explain these concepts to you in detail. And in the next session, actually, we will have a very hands-on kind of a scenario where I will actually show you how we can go about designing these types of antennas. Okay, so dipole would be a very simple case, but we will also design Yagi Udas, we will design log periodic, and these are just names, but we will specifically see how their parameters or how their length parameters, etc., make a change into gain, make a change into impedances, etc. Okay, these are very interesting topics that we'll touch upon. This is something that we will simulate on our own on the software called FECO. Okay. Yeah, I think this is some. Yeah, I think Sanket would do a good job in explaining. Already we are above time. It is 8:30. Uh, yeah, I will be happy to take a few questions if there are any.
Sir, does all parameters vary with different types of designs of antenna, or they are?
Yeah. Sorry, continue your question. Yeah.
No, so this is the same question. Does parameters vary with designs of antenna, or do we have any standard for which we look in every design of an antenna?
Okay. It is a good question because uh, basically what we do is when we are designing a dipole antenna, we would design it it is usually called as the lambda by 2 model, where this length element, the entire length element should be lambda by 2 of, and because it is for resonating cases. All right. While doing the design, you have to check what is your operating frequency. And yes, by that I mean that for all different types of antennas, you get a different use case. So in some cases, you would not be looking for directionality. In some cases, you would not be looking for very high power, but you will be looking for subtleties like circular polarization, or I want beam width to be in that specific range, etc. So yes, every element in the antenna would decide what is my output. May let it be, if I was just to fold this antenna a bit by 30 degrees also, no, it would drastically change my impedance, and that is very interesting to observe in simulations, etc. Okay, so the short answer is yes, and why it happens, you should simulate and see and get a feel for yourself. Okay, any more questions? Is there any question in the chat box? You can just unmute. These sessions are meant very informal. Okay, I'm not any professor. I'm just someone of your age who happens to have a bit more experience into this field, and we are just trying to get into the same level. Okay, there is a lot of learning curve that comes into play when you are studying antennas. It might sound very overwhelming and very engineerish, but when you try and understand what wonders it does for the radio astronomy part, you will get equally excited as I would. Okay, and my job would be to keep you excited through the.
Viren, you mentioned the concept of fractional width. So can you please explain that why is the fractional width calculated in an initial stage, and what values of that width is preferred for an antenna structure?
For an antenna structure, okay. Your last thing was not audible to me. Can you repeat?
And I asked that why do we calculate fractional width, and what values are preferred of the fractional width for an antenna structure?
You mean fractional bandwidth, right?
Yeah.
Okay. For this, okay, let's just. Usually what happens is that when you are comparing different types of antennas, you have a problem of scale. Okay, I'm not sure where it was. Let me go to the slide. And what fractional bandwidth does is it just removes the removes the necessity of a scale. Why? Okay, I just show you the. Okay. Yeah, so a fractional bandwidth would mean that usually fractional bandwidths that are preferred should be towards the higher side. Why is it? Because if we want a high performing, or sorry, towards low. Okay. But what fractional bandwidth does is, I'm not sure if I can answer what type of fractional bandwidth an antenna needs. It is because it is a characteristic of each antenna. But why we do it is because then we don't have to deal with this type of a scenario where I have to scale it out and have to subtract each term. Fractional bandwidth is just independent of scale. Okay, whenever you take fraction, usually whenever you take fractions or do ratios, it is because that you neglect the scale at which we are working. So a same patch antenna which is working at say 985 to 1 megahertz, same I can do with 985 to 1 gigahertz also, and roughly I would get the fractional bandwidth to be same. Okay, so with considering my design parameters are not changed too much. So all you're doing with fractional bandwidth is you are just neglecting what frequency e to the power how much, okay, 10 to the power, sorry, 10 to the power how much. You just neglect that and you just see how much difference it is, and that is what helps us in understanding, rather than when we are comparing large types of antennas. Yeah.
You
Did I
mentioned
answer?
one other type of bandwidth also. Can you explain about that also? Like, how is that implemented in the antenna study?
What? Can you please repeat again? One type of antenna.
You mentioned one type of other bandwidth also. So can you please
Fractional
tell about
bandwidth.
it? Yeah, fractional bandwidth.
Yeah, fractional bandwidth is the same thing that I just said. Uh, Percentage bandwidth again would be just multiplying it by 100. That's all. I mean, how much percentage? I mean, it's in the name, right? The exact use case, even I haven't used it very much. When throughout my projects, I did not have to tell what was my fractional bandwidth or what was my percentage bandwidth to anyone. So I would not comment on the actual use case of it. But of course, fractional bandwidth, uh, as a definition, I have put it. But usually, when people are asking, they would ask you about what is the bandwidth rather than fractional bandwidth, etc. These are very technical terms when it comes to antennas, and it does not help you actually design, because then you need to know exactly what scales you are working on. So for me, at least in my experience till now, I haven't used fractional and percentage bandwidth in my case. But it is a good way. It is a more professional way of saying at what ranges my uh, antenna is actually working on.
Thanks, Viren. Like you were explaining that we are use polar plots to study the radiation pattern, right?
Yes.
So, is the polar plot the only tool that we use, or are there any other tools also that we use? But like they are very high order, and we like don't use them on a practical basis.
Okay, in tools, yes. Usually, what you would do is, okay. What I will do is I'll stop sharing so that I can have a nice conversation. Okay. So usually, in tools, if you are into the instrumentation, or if you are into simulations, the characteristics that I showed you right now. Okay, are you asking about polar plots itself? Only polar plots, and you're asking if there is another way of looking at it?
Yes, I'm asking that specifically.
Okay. Sorry. Yeah, thank you. So in polar plots, basically, yes, polar plots is I think the only way of looking at the electric field, because it becomes easier rather than looking at all the theta and phi's that are available in the spherical coordinates, and it gives you roughly, usually any guide or anyone would just ask for what is the who would like to see the polar plots. So there is no, to my experience, I haven't seen anything that is more higher order, and I don't think there is also a requirement, because it is actually doing the job perfectly fine. And in the polar plot itself, you can also check what is your radiation efficiency, which is that towards what scale of angles is my radiation being maximum or is radiating efficiently. Okay, so you can manipulate your plot. That is, you can have only a theta, have only a phi. That also allows you to measure what is my polarization gain. Okay, if you are just looking at one side, one actually polarization would help in 3D, but of course the polar plots of course have an option to allow you to see how much polarization gain you are receiving. Is it right circular more, left circular more, or is it linear molar, z cross more, cross and co more, all those things. So yeah, I think polar would be the best option to analyze gain of an antenna.
I see. So you mentioned that we can calculate radiation efficiency using the polar plot. So in any of your examples, can you show that how we do that, or does it require computation?
No, it does not require computation. All I have to do is I have to see my radiation plot through all different angles. Okay, I'll have to start my. It would require some time to just run my program of this particular antenna. What I'll do is I will put the plot into the Discord, okay, and you'll be able to see how it looks. I have some pre-plots available, which is not available with me right now, but I'll definitely show you. I'll put it on Discord. I think we are connected through Discord, right?
We have joined the channels, but we are not sure. Like, would you put it in the general group of the like where the announcements are made, or in which group?
I'll ask them accordingly, where everyone would where everyone can have a look at what exactly radiation efficiency, what exactly it means. And of course, I've missed on a few points here, that is explaining what S parameters and ground plane is, because I felt that was too technical for us today, because Nakshatra team told me that most of them won't be knowing anything about antennas. So I remembered my time when I was first introduced. So I think this was apt enough to cover for a day, right? Not confusing it much and not making it too overwhelming for people to understand.
Thanks,
Yeah.
Viren, for this wonderful explanations.
Oh yeah. Thank you so much. Thank you so much. I would like to have feedback from you guys as to how the session was. And even the Nakshatra team can just tell me how, if there is some improvement needed in the time, or if I am prolonging a few explanations too much. I would like to know.
Yes, it was a very nice session. Thank you.
Oh yeah, thank you so much.
It was
I
an
do have
amazing
one.
session. Thank you.
Thank you. Actually, it got a bit late. I'm sorry. There was a crash. Uh, but I would like to thank, oh yeah, of course, I would like to thank Nakshatra for giving this opportunity to discuss with you guys. I mean, I just like collaborating. The collaboration spirit is something that I enjoy, and I like discussing topics that I've learned previously, which adds into my knowledge more. Right? Yes, I'm sorry. Did I come in between of someone? Was someone speaking? Yeah. Oh, see the messages also. Yeah, okay. Vishwajit Jana has answered. So thank you, Naren. Partially correct. Yeah. What values of fractional width is preferred? Yeah, we answered that. Okay. Yeah, okay, Divyanshi, yes, of course, we will not prolong it too much. If we have no other questions, we will end it for today. I think if someone from Nakshatra is there, we can stop the live feed and end the meeting today. And I hope to see you guys soon in our discussions about Maxwell's laws and all other depth topics. Of course, we missed Sanket today. He'll join in soon and we'll have a discussion with him also. Okay. Yeah, good. Should I take leave? I mean, is there anyone from Nakshatra here?
So yeah, I think if there is no doubts, we can